Hello, everyone. Time to get ready for another lab. So this week, we're going to be continuing our caffeine extraction by purifying our products. So last week, we've generated a nice crude caffeine powder that should be sitting in the back of your hood. This week, what we're going to be doing is trying to purify it and characterize it to see how well our purifications worked. So our purification is going to be accomplished via two main methods. The first, we're going to take our crystals and dissolve and recrystallize them. And then we're going to go ahead and sublimate it or drive it into the gas phase and deposit it back onto a cold finger. Now, when we do this, our caffeine crystals should become more pure at each step. And we're going to characterize how well this worked using two methods. We're going to take a small amount of our crude product, the one you made last week, a recrystallized product, which we'll have generated halfway through lab, and then finally that pure caffeine that we get from sublimation. And we're going to test it with two major methods, TLC and melting points. So let's go ahead and dive in. So whenever we have a impure solid, one effective way to try and purify these solids is going to be slowly dissolve your sample. Now, when I go ahead and slowly dissolve my sample, I can go ahead and leave the impurities behind in the solvent by recrystallizing it. And this whole process is known as recrystallization. So the first step we need to do is choose a solvent that will barely dissolve your sample. So if I want to barely dissolve something, typically we're going to end up doing this with a hot or boiling solvent. Because again, things should dissolve more easily when I'm working with a hot system. And this will make sure I can use the bare minimum of solvent that I need to. And one of the reasons why this is important is that the second step is going to cool the system down and try to encourage the formation of crystals. Often we're going to add a secondary substance to help drive this process. It could be something like simply adding a seed crystal, or essentially a little bit of the pure solid, which acts as a nucleation site for our new crystals to form behind. Sometimes we're going to add a second solvent, which will make this solution a worse place for our crystals to be. And as we do this, what should end up happening is that if I form these crystals relatively slow, it should make sure that the only thing present in the crystals is my substance. Because if I do this process nice and slow, any impurities should be left behind in the relevant solvent. But again, because I don't want to leave much of my solid behind, I'm going to try and make sure that I have as little solvent, I use as little solvent as possible to guarantee that only a minimal amount of my desired product is left in solution. So for our specific system, what we're going to be doing is we're going to use a solvent mixture of acetone and petroleum ether. So what we're going to do is we're going to first dissolve our substance by heating acetone. So again, acetone is a mildly polar solvent, and our solution is mildly polar, so it should dissolve fairly nicely. But the trick here is that if I use the hot acetone, I can use the bare minimum amount of acetone it takes to dissolve my substance. That way, when it cools back down, I only leave a little bit of caffeine dissolved in the acetone. Now, to try and drive the system back into forming crystals, we're going to do two things. So first, we're going to cool the system. But the next major thing we're going to be doing is adding petroleum ether. So petroleum ether is a very non-polar solvent, which will essentially make my whole solution much more non-polar. This is going to drive my polar crystals out of solution so that they're going to want to reform. And if by cooling the system, I can go ahead and, again, make the formation of the solid much more favorable than these crystals being dissolved in this new mixed solvent. But one of the major things we're going to need to do is, because both acetone and petroleum ether are going to be fairly volatile, meaning they'll rapidly evaporate, we're going to need to use a piece of cork to go ahead and cap this container to prevent any of that solvent from disappearing. Because if that solvent disappears, this means that I'll start crystallizing my impurities back into my crystal. And I don't want to do that either. So we need to have enough solvent so we can dissolve those impurities, but not so much solvent that we're going to dissolve our desired product. And that's the real trick in this method. If you end up evaporating all of your solvent, you're going to need to essentially restart the process, redissolve, and recrystallize. However, if you end up having no product form at all, this likely means you have too much acetone and the system essentially wants to stay dissolved. At this point, you have no choice but to heat the system up and dissolve that acetone back. But if you hit that perfect middle ground, you'll have some solid and some solvent. At this point, we can do a quick gravity filtration with our folded filter paper, which should remove any of the solvent and leaving us behind with just this solid. So we're going to go ahead and then take that solid off of the filter, go ahead and weigh it and put it into a container, weigh it and let it dry before we do the next major step, which is sublimation. Because it turns out caffeine has a really unique property. It turns out that it can sublimate. This means that it will readily go straight from the solid phase to the gas phase with never turning into a liquid in the meantime, straight from solid to gas. This is a really useful feature for us to go ahead and use because almost everything else that we're going to be that would show up as an impurity is either going to stay as a solid when heated or it's going to turn into a liquid. This means that by heating this system, I'm going to leave behind any solid impurities, get a gas that comes off of my caffeine solid, which I can go ahead and deposit onto a cold surface. The one we're typically going to use is called a cold finger, literally because it is a glass tube that gets rather cold. So you can see here a depositing of iodine onto a cold finger, which really shows off the system very well because iodine is so beautiful and purple. In order to accomplish this, you can go ahead and typically fill that cold finger with ice like we did last week in the rotovap, or you can go ahead and fill it with flowing cold water. This time, we're going to be using that flowing cold water. So what we're going to do is we're going to go ahead and place our caffeine into a sidearm flask, which looks rather like this Erlenmeyer flask on the right. The only difference is it has a tube on the side where you can go ahead and hook up a vacuum line. We're going to then run cold water through that cold finger. So again, using the water line in your hood, this should help that solid deposit as it sublimates off from the bottom. The flask is going to be connected via that sidearm to a vacuum aspirator. This will essentially help pull any of the gas as it forms off from the bottom of our container up towards the top. Again, the goal here is it should end up helping pull the caffeine past that cold finger where it will recondense. If you have a lot of caffeine or your cold finger isn't quite cold enough, or you essentially have a little too much aspiration, some of it may end up going into the aspirator, but the cold finger should catch most of it. This also has the side benefit of acting as an outlet line for our system, which more or less just helps make sure that we're not heating a system under closed pressure. We're going to go ahead and sublimate that solid using a Bunsen burner. So we're going to essentially connect that flask, clamp it in place, and then run a Bunsen burner over the bottom to essentially remove any of the caffeine off the bottom. When we do that, most of it will recondense back on the cold finger. Some will go ahead and condense along those sides. So you're going to very carefully run that Bunsen burner along the sides to try and get as much of the caffeine to deposit onto that cold finger. Some of the things to watch out for, though, is that there will often be tubing associated with both our cold finger along with that sidearm. So we don't want to let that flame get too close to the tubing. This is how the hoods catch fire, and it pretty much happens at least once every year. Just go ahead and call me over. The fires usually aren't too bad. The other thing is you don't want the heat to get too near that cold finger. Otherwise, you'll essentially evaporate or sublimate your solid off of that cold finger. Once we've done this, we can go ahead and pull that cold finger out of our container after turning off the vacuum and go ahead and scrape all of our caffeine onto a weigh paper and then measure how much caffeine you produced in on the balance. Now, what we're going to also want to do is characterize our samples. So we're going to go ahead and do this via two ways. The first one is you're going to go ahead and from each of your three samples, you're going to save a single crystal of each. So uh, one crystal from your crude product, one crystal from your um, recrystallized product, and one crystal from your pure, which you should have plenty of at this point. You're going to go ahead and dissolve each of these in a couple of drops of acetone, one or two, not much, and then you're going to go ahead and spot it onto a TLC plate. So again, you're going to go ahead and, as usual, draw that spotting line. And unlike last time, we're going to be putting 3 spots on the plate, all in parallel. That way, as the sample runs up, you should be able to compare all of your various samples one to another. So you can get kind of a direct comparison. So in addition to looking at the RFs, you should be able to rapidly say, I've got 1 spot, I've got 2 spots, they're all the same, all have the same RF, they all have different ones. It should make for a rather quick and rapid analysis. So we're going to end up using acetone as our developing solvent, or again, our mobile phase. But one of the things I want you to keep in mind, these 3 lanes should all contain at least 1 spot of caffeine. And all those spots should be all in a row because they should all have the same RFs. But when you think about what would impurities look like, would they change the spot? Would they add more spots? Would I add fewer? What would we expect to happen? Now, part of the issue here is that the caffeine spots won't be nearly as easy to spot as when we were working with our spinach extract. So this is where we can really use that UV vis lamp. It will help us identify our spots, and you can go ahead and use your graphite pencil to circle any of the relevant spots before measuring the RF. There's also another technique we can go ahead and do, which is after you've tried the UV vis lamp, I want you to go ahead and put your plate into the iodine tanks that should be sitting out. Just go ahead and place it for about 30 seconds. What should happen is because iodine also sublimates, each of these tanks should be rich in iodine vapors. And if you leave it in there for 30 seconds, the iodine will preferentially bind to that caffeine molecule as it really likes these kind of aromatic rings. And so what should be left behind for the next minute or two is a little bit of a purple spot wherever your caffeine is present, as well as any other potential impurities. So we can use these 2 methods to go ahead and try and visualize our caffeine spots, and then use these TLC plates to address our purity. The other thing we're going to do to assess purities, we're going to go ahead and use our melting points. So melting points really take advantage of the fact that if I have a very pure sample, the melting should all occur at a single temperature. So the melting should all occur exactly at that melting point, less than 1 degree separation. But what ends up happening is the more impurities present in the sample, the wider range over which that melting will occur. It will often start at a lower temperature and it will end at a higher temperature. Sometimes it will only start at a higher temperature and end at the same one. Sometimes it will start at the same temperature but end at a higher one. Most of the time, however, it's going to start lower. So expect your melting points to start to occur a little bit lower than the literature values. Based on the relative purity, you'd expect this to either be much below or only slightly below the literature value. And when actually running these melting points, usually what we can do is if we know the identity of our sample, I know I have caffeine, you can use that literature melting point and rapidly heat the sample till about 20 degrees below the melting point. Then you can go ahead and slow down the sample and heat it very slowly until you get to exactly the right temperature. What I would highly encourage you to do is on Canvas under Appendix 3, there is a nice table of what the heating curves at various temperatures various heat settings look like. So more or less exactly how fast I'd expect the temperature increase for various temperature ranges at various settings on our melt temps. Also, another major advantage is most of the melt temps we have can go ahead and analyze 3 samples simultaneously. Guess how many samples you have to analyze? So what we're going to be doing is we're going to be taking our crude sample, our crystallized sample, and our pure caffeine sample. We're going to go ahead and collect that sample into a melting point capillary tube. What I would highly encourage you is as you generate each of these products, go ahead and quickly collect that melting point and go ahead and save it in your drawer and go ahead and label it lightly. Again, if you use tape to label these, I'd highly encourage you attach that tape very lightly as as the tubes have been known to break when trying to remove the tape later. So this means by the end of the lab, you should have 3 nice capillary tubes, one for each of our 3 products. However, part of the issue is that since caffeine sublimates, if I want to watch the melting point, I've got to find a way to seal the top of the tube. This way it will prevent any of that gas from releasing. We're going to be doing this using a Bunsen burner to literally melt the top of the tube, very similar to how we made our TLC spotters. And by melting the top of the tube, this should essentially seal it from any vapor being released. Now, one of the big things is oftentimes by the point you have all of your tubes made and and everything else cleaned up and packaged, we're usually at about the end of the lab. So oftentimes we're going to end up encouraging you to collect your melting points outside of class because these can take 10 to 15 minutes to collect. But we are going to require that you come in with a partner. It could be a partner from class or it could be a friend from outside of class. The major thing is we want to make sure that if you're that you're not working in the lab alone, as this can become a safety hazard. Even if you're not playing with any chemicals, all it takes is for somebody to left, say, some dichloromethane out, and you start to feel a little bit lightheaded. Also, in addition, you are going to want to come in during normal office hours when the room should be left open for you. All right, so before we do the lab, as usual, things we need to do to prepare. I highly encourage you to read Morg's chapter 15 and 16. So this covers the processes of both recrystallization and sublimation. As well as I said, take a look at Appendix 2. So this is a reminder on how to do sig figs, which will be very important when you're doing some of the analysis for this lab. Specifically, we have to calculate percent yield and percent recovery. Appendix 3 also gives some very good suggestions on what heat settings to use for your melting points, as well as watch this video. And don't forget to go ahead and complete the Canvas pre-lab quiz before lab, write your pre-lab notebook, and answer any questions to consider. Also, don't forget that the caffeine separation scheme worksheet is due in class at the very beginning. Once we actually get to lab, as usual, we're going to meet in the chem lounge. We're also going to have our first round of safety presentations. So if you're up first, just a reminder to make sure you're working on that. Then first thing you're going to do is analyze your crude product. This step often gets skipped. You're going to want to know exactly how much mass you have to start from. This will help you calculate both your yields and your crude recoveries. Then we're going to perform that recrystallization. So again, remember, we're going to need to make some we're going to need to heat up some acetone, and you're going to want to add only the bare minimum to dissolve your sample. Then we're going to add that room temp petroleum ether, then cap your flask and let cool till you see crystals form. Again, an ice bath might be useful here. After this point, you're going to go ahead and filter and collect your crude product. Again, reminder, when you're filtering, you're going to want to make sure to use a cold petroleum ether to rinse your crystals. All right. So while you're setting up the next part, you can go ahead and let your crystals dry before you take your crystallized product mass. And again, you can use this to calculate your percent recovery. Then you can go ahead and start your sublimation. So again, uh, at this point, you're going to go ahead, set up your sublimation apparatus, and then heat the system till all you're left with is pure caffeine crystals on your cold finger. At which point you can go ahead, scrape that off, go ahead and mask them out, and figure out your overall yield on the process. But again, big thing, don't forget you need to run the TLC. So you can go ahead and take your little bit of each of your three samples. Um, and then run your TLC while you're finishing cleaning up. Also, make sure to seal your three melting point tubes. So you should have already made your three tubes. Don't forget to seal them so that you can run your melt temps later. Also, this is the first lab where you are submitting a final product for a grade. So your grade will be related to your overall purity and yield on this product. So don't forget to go ahead and turn in your labeled product, including the mass. Then you can go ahead and clean up. If you have any extra time, you can perform melting point analysis, but expect to save a little bit of time outside of class. Often the sooner the better, so you don't forget about it before fall break. So some big reminders when doing this. As you may notice, there's a lot of steps to this, including several steps where you have to go ahead and wait for things to heat up, cool off, or cool off, or even just dry out. So make sure you plan your time accordingly and go ahead and always get the next step ready. If you ever find yourself sitting around, that would be the time to do math. You can go ahead and wait for your math if something else needs to be done. This is also a big one. Oftentimes, students will forget to collect one of their crude samples. Remember, you should have three sets of TLCs and a TLC of three different samples and three different melting points. So make sure you collect all three of those. Now, again, we're playing around with a lot of hot systems, and especially this time, playing with Bunsen burners, both to seal our melting point tubes and for the recrystallization. So watch out when handling the heat. Also, you're going to want to make sure to cap your Erlenmeyer during your recrystallization to prevent any solvent loss. If you lose too much solvent, if too much of your petroleum ether evaporates, you're going to have to rerun the system. Now, especially because we're going to be playing with Bunsen burners, don't forget petroleum ether and acetone are both very flammable, so make sure that all of your organic solvents are away and capped before you pull out the Bunsen burners for sublimation. And again, while performing your sublimation, make sure you have water running through the cold finger, otherwise your sample will disappear. And you keep that Bunsen burner away from all of the rubber tubing. Otherwise, you can get a mild hood fire. And again, don't forget, make sure to properly label your final product. It's very important to include the mass of your caffeine, as this will be part of your grade. And again, the only thing you should be doing outside of class is going to be the melting points. If I hear that anybody did anything involving any chemicals outside of class time, you will be subject to losing points. All right, so once you're done with lab, big things you have to do, make sure to go ahead and post your post-lab notebook scans by the end of the week. I do want to see your melting points in there, preferably. Remember to turn in your PyMol lab, which is, again, due this Friday. Also, coming up, you're going to be writing a results and discussion section based on this lab. So this is due on October 21st. So I'll give you 2 weekends to do it, but one of those is going to be fall break. So again, trying to get a little bit of work done over the weekend, which means trying to collect as much data beforehand. Full guidelines for the results and discussion is online, as well as, again, if you have not already watched them, the videos of how to write figures and how to write a results and discussion section. So that's the major things we need to cover for lab this week. Best of luck, and I'll see you there.